This video lecture is on molecular geometry. We've been working on this in the lab here for a while. This is going to be some of the content from the textbook that relates to what we've been doing in the lab, talking about bonding theories and how that works. So this is Chapter 9, Sections 1 through 3 in your textbook. First of all, when we think about molecular shapes are a way to try to figure out reactivity and, more importantly, polarity and how molecules interact with one another. So when you think about the structures, it's important to know their general formulas. And here are some general formulas that you can see here on your screen. It's important to see that you've got the general formulas of what goes together. So if you look here on the linear part, it has like an AB2 here at the bottom. That AB2, that A represents the central atom with two atoms that come off of it. That's the B2 part, and that's linear. When you see this AB2, this is the same general structure, AB2, because it has a central atom with two atoms that come off the side, but notice its shape is different. This is AB3, so it has a central atom with three bonded off of it. This one is also AB3, but the shape is different. You see how the other groups get pushed down to the bottom, and the nitrogen group sits at the top. This is yet even another AB3, and it makes a T-shape. So what accounts for the same general formulas, AB2s, AB2s, why do you see different shapes between the different molecules? Well, it has to deal with the bonding electron pairs and the non-bonding electron pairs and how those look. So when we talk about this, we'll see electron domains. So we refer to these pairs as electron domains. So in this particular structure, in a double or a triple bond, all the electrons are shared between the two atoms are on the same side of the central atom. They count as one electron domain. So if we look at this particular structure, this has 4 electron domains because there are 4 total bonds that go around it. So this is an AB3 structure. If you were going to try to talk about its general geometry, we'd say this is AB3 because it has a central atom and 3 around it. Notice though on the A, there are 2 electrons that are not in a bond. That's a non-bonding pair. That's important as we get towards geometry. So the way we can explain this is we have to have a theory to explain the molecular geometries of molecules, and it's called the VSEPR, Valence Shell Electron Pair Repulsion Theory. This just says that when you get electrons together, they're going to try to get as far away from each other as possible because they're all negatively charged. So this is a molecule of CCl4, carbon tetrachloride. That molecule itself, those chlorine atoms want to repel away from each other as much as possible. And you can see that in the space-filling model. It makes a tetrahedron. Or think about a tripod on the bottom with another point to the top. This figure at Table 1 in your book is absolutely critical. This is, if I were going to take notes on something, Table 1, this is really good. It talks about electron domains, and it talks about how it works around the central atoms. So if you look at the geometry here of linear molecules, it's 180 degrees between the two of them. Trigonal planar, it has 3 bonding sites around it. Flat, no unshared pairs. This has 4 bonding sites around it, 4 sp3s. This has 4 bonding sites around it, no unshared pairs. So as you see the geometries of this, the number of bonding pairs are important, and the numbers of non-bonding pairs are important. So how do we figure out what the shape is? First thing you want to do is count the number of domains on the structure. Then the geometry corresponds to the number of electron domains. So NH3 is ammonia. When you do its Lewis structure, it has 4 electron domains. So it kind of forms a tetrahedral that you can see here with the different sides on it that we saw earlier. You can see the notation over here with the lines that go in and out. You can see right here how it has the dashed lines, meaning that it's going into the board, and then you've got the solid wedges kind of coming out towards you, and then one off to an angle. That's a way that we can draw something three-dimensionally on our paper when we depict the models. Now, does it make a tetrahedral shape? That's the question. Well, when you look at this, you draw that Lewis structure and you see the electron domains. There are 4 domains, but the difference is you've got a non-bonding pair on the top. It's not only the atoms in the molecules, but the non-bonding pair. If you see on this ammonia molecule, there is an unshared pair that's on the nitrogen. And as we'll see here in a second, these unshared pairs, or these non-bonding pairs as they're referred to in your book, take up more space than the bonding pairs, and they force the other groups to the bottom. So we don't see this take the form of a flat triangle like this, where it all spreads out evenly. We see the other groups push down to the bottom, and that's all because of the non-bonding pairs that we see. So, thinking about molecular geometries. If we take one of those away, we get trigonal pyramidal. Trigonal meaning the 3 faces, and then pyramidal like the pyramid. And then we have bent. Now this is where we have an electron domain where we have unshared pairs that force the other groups down. So, thinking about linear. A linear molecule, this is the general formula here. This would be AD2. Let's go back one. This would be AB2. So if you think about those general formulas, A is the central atom, B is the outside or surrounding atoms, and there's 2 of them. Notice in this example there are 2 bonding domains and there are 0 unshared pairs. So according to the Vesiper theory, those bonding sites are going to want to get as far apart from each other as possible. This makes it have a linear geometry. This is trigonal planar. Notice trigonal planar has 3 bonding domains around it. Non-bonding domains are 0. This is boron trifluoride. That's an exception to the octet rule. There are no unshared pairs on the boron, so the fluorines spread out into a flat triangle. That's different here for NO2. NO2 has 2 bonding domains, and it has an unshared pair. See, that unshared pair on the top of this molecule ends up taking a lot of space. Just by looking at the size of it, this non-bonding orbital, this hybrid orbital that we'll talk about later, ends up taking up more room, and it forces the oxygens down, bending it. Unshared pairs bend down groups. So this kind of shows you the size of this. If it's a bonding electron pair, it's kind of an oval. But notice on the non-bonding pair, it's really big on the top and takes up a lot more space. You can see some examples of bonding and non-bonding sites. This is methane, which has 0 unshared pairs. So notice how it spreads out into the tetrahedral. This has 1 unshared pairs, and the bonding angle is 107, so it bends it down from 109.5. This water molecule has 2 unshared pairs. Notice how much it increases the bonding angle. It pushes it down even more, making water bent, which helps account for its polarity and how it interacts with other molecules. So the more unshared pairs you have, the more it's going to bend those groups down. Multiple bonds get a little trickier. Think about how it looks. These double and triple bonds put a lot of electron density on that central atom. So they do affect bond angles. So if you look at this bond angle here, 124.3, 124.3, that double bond does affect and bend those chlorines down even more so than what the single bonds do. This is a greater bond angle. So double bonds bend it down more than even a single bond would, because there's just more electron density there that takes up more space than those single bonds do. Thinking about tetrahedral domains. 4 bonding domains, but no unshared pairs. It spreads out into the tetrahedral. And again, thinking about those bonding domains, if we did a structure of this, this would be AB4. And again, that was spread out into the tetrahedral. This is NH3 ammonium. It's got 3 bonding domains. It's got a non-bonding domain, and that forces those other groups down, so it makes this trigonal pyramidal design, so it pushes it down to the bottom. Down on the bottom with water, you got 2 bonding domains and 2 non-bonding domains. Again, that forces the angle down even more because they're taking up more space, and that would be water. This is a little bit different here with our trigonal bipyramidal domain. These are going to spread out as much as they possibly can. The 2 ways that this can actually go is axial and equatorial. Now, the 3 equatorial positions, equatorial, think about the equator as it moves around the Earth. These 3 are all around lengthwise, like roundwise, like the Earth equator would be. Axial position on the top and the bottom, think about an axle on a wheel, and the central atom is like the wheel. The axle goes through the middle of it, perpendicular to it. So this is a way to think about the geometry. This is unique to this particular molecule. If you think about how this looks shape-wise, this is A, and this is B, and it's got 1, 2, 3, 4, 5 groups on it. So this would be an expanded octet. So this is a little bit different shape, and if you get that expanded octet, this is a typical geometry that you could see. This is an example of trigonal bipyramidal domains. This is one of those expanded octets with sulfur, sulfur tetrafluoride, and it's got an unshared pairs on the top. So notice when they're trying to bend, they're going to go equatorial and axial here, as you see it. Lower energy conformations result in non-bonding electron pairs in the equatorial. It makes rather than those axial positions. So notice those angles here. You've got an unshared pair forcing those other 2 fluorine groups down, and then you get not quite 180s for the other 2 fluorines. So those domains still affect these hypervalent structures that we can see in the 3rd energy level and below. Now, how do you figure this out with these different shapes? If you've got 5 bonding domains, that means we're going over the octet. Here's PCl5. That's trigonal bipyramidal. And then you've got this seesaw shape with SF4. Seesaw because it looks like a seesaw because it goes back and forth. That's got 4 bonding domains, 1 non-bonding domain. So we get the bent action that you see there. T-shaped, you've got chlorine trifluoride. You got 3 bonding shapes, and then you have 2 unshared pairs. And again, that T-shape is going to force those other groups away. Xenon difluoride, that's going to have 2 bonding sites and 3 unshared pairs. These are extreme examples of molecular geometry. But one thing's consistent. Unshared pairs are going to put more strain on the bond angles and force them down every time. Octahedral is another expanded octet. You've got 6 different bonding domains. As you look around it, no unshared pairs. It's going to spread out and be octahedral. That's sulfur hexafluoride. When you start adding unshared pairs, you get other odd shapes like square pyramidal. Forces the other groups away from it, and it sits on the top. Then you got square planar if you got 6 bonding domains, 4 bondings, 6 electron domains, 4 bondings, 2 non-bonds. Again, they force everything else away, and they produce a square planar geometry, and you'll put one of those together in the lab as you go through it. So it's really important to recognize not just the number of electron domains, but which ones are participating in bonding and which ones are not participating in bonding. These larger molecules, they get really complex with the geometry. You can look at individual geometries and isolate atoms when you get to bigger molecules and talk about the geometry around it, but it's easier to talk about the isolated parts. And it talks about when you see atoms like this central carbon in the middle of this structure here at the top. This carbon here, that's trigonal planar. It's got 0 unshared pairs, and it's got the 4 bonding domains on it. So you would think about that being trigonal planar around it. You can look at some others, like this particular carbon here. That's going to be tetrahedral because it's got all the groups around it. So again, or excuse me, trigonal planar, because it's got 3 groups around it. So as you try to lay this out, it's tougher to figure out what it is based on the structure. So that carbon there has 1, 2, 3, 4 bonding sites to it. So that would be tetrahedral. I said trigonal planar, it should be tetrahedral there. Now, the thing about this that it really affects is polarity. That's bond dipoles. So shape and electronegativity are the 2 biggies. Shape and electronegativity are big. These are both polar, this is a polar bond between carbon and oxygen on both sides, but they're pulling with equal force in opposite direction, and they cancel each other out, just like vectors in physics. Notice the electron density is evenly spread out, and there is no dipole moment. Now, when we get to something, in this case, of a polar molecule, when we bend the molecule down, now we get both arrows adding together. Now, we're not doing geometry to where we do the trig functions to find the resultants, but notice how both of those arrows are pointing up to the red atom. So they're both pulling that way, and notice that the electron density here in this structure is really centered towards the top. That's because both arrows are pulling electrons, adding together in the same direction. This is definitely a polar molecule. Bent molecules are always polar because of their geometry and their non-bonding pairs. Take a look at some of these examples. HCl is polar because it's pulling towards the chlorine. This is nonpolar, BF3, because the fluorines are polar bonds with the boron, but they all cancel each other out because they're equal and opposite in direction. CCl4 has polar bonds all over the place, but they're all pulling in equal and opposite directions, making it nonpolar. NH3, notice how all of the arrows are adding towards the nitrogen. That makes it polar. CHCl is polar because one of those bonds is more polar than the rest. So there's a net pull of electrons to the chlorine. We'll talk more about overlap and bonding as we get into the next sections. Now, one thing to think about just kind of in generalities, if you have unshared pairs, it is likely polar. Unshared pairs, likely polar. Now, that's not a hard and fast rule, but that's a generality that you can look at. Another thing that you can think about, if all groups around the central atom are the same, that means they're going to have pulls for electrons. It's usually non-polar. The opposite of that is also true. If they're different, it's usually polar. Those are some things as you look at geometries as you go through this that you'll find are pretty true generalities that you can use to help make some predictions on what's happening in polar molecules. Take a look and we'll work on some homework problems tomorrow and we'll check those out. Thanks for watching.